G'day, Chris here and welcome back to ClickSpring. Among the many engineering achievements demonstrated within the Antikythera Mechanism is one that's largely hidden from view, and that's the ancient Greeks' ability to create very precise small holes. The device is full of them, and they're all critical in one way or another to its ability to function. To receive locating pins, to act as reliable bearings for the gearing assemblies, and to form the starting point of the many square openings found in the various parts. Now, the ability to put a small, accurately sized hole exactly where it needs to go is no simple achievement even today, so it's worthwhile investigating just how it could have been done in the ancient world. The evidence suggests that the vast majority of the holes in the machine were drilled, and a likely candidate is one of the oldest drilling tools on record, the pump drill. I've designed this version to be a genuine working tool with interchangeable drill bits, so it'll need to be durable and robust enough for daily use. But it will also need to be light and sensitive enough to cover the full range of holes found within the mechanism. Where practical, I'm using the raw materials known to be available in the period, like for example raw copper and tin to make bronze and a local oak for the timber components. Where it gets a little difficult to source authentic materials, or if the material choice has no significant bearing on the outcome, I've used some modern substitutes. Like for example, mild steel as a substitute for wrought iron, HDPE for the casting pattern, and a heavy gauge fishing line in lieu of a gut-based cable. And if you'd like to build one of these for yourself, the plans are available as a free download, so be sure to check the description box below for the link. Okay, so first up is the flywheel, which I cast from bronze. Traditionally, the pattern for something like this would be made from timber, but as you can see, HDPE is a lot more fun to turn, and best of all, there's no dust to clean up afterwards. Now, so far in the build, I've been using a modern lathe for all of the turn parts, and of course it raises the question, what was the equivalent technology of the day? Well, certainly there's enough evidence on the historical record to suggest the widespread existence of turning technology. In fact, the Roman author and engineer Vitruvius, writing at around the same time that the mechanism was lost, mentions lathes in a completely offhand manner, expecting the reader to be thoroughly familiar with the idea, as if the technology was so commonplace that it barely required explaining. As it happens, the Antikythera Mechanism may in fact be the very best evidence available to establish the full extent of that lathe technology, at least as it relates to smaller scale engineering. And it's something that I'll be covering in detail in a later video. Okay, so with the pattern complete, I rammed up a sand mould in preparation for the pour. So that's the sand mould ready to go, and the crucible is charged with weighed quantities of tin and copper to give an 85-10 bronze. The remaining 5% will be made up with lead and added once the melt is well established. The pouring basin and gating will be thrown back into the crucible for the next melt, but the feeder and riser will be used as a source of round stock for other parts, and you'll see them being used later in the video. Much like the small parts vise, I think the as-cast surface makes a great contrast with the turn surfaces. And you can see that this bronze behaves very much like a free cutting brass, which makes it perfect for freehand turning. And that's the flywheel complete for the moment. Next up are what I'm calling the collets, the parts of the tool that'll hold the various drill bits. I cast some long round stock from the same bronze as the flywheel, and then turned it down to an appropriate starting diameter. I then formed the basic collet profile. Now the precedent of square drivers operating in square holes is well established within the mechanism. So I've used the same idea for this drill design. And whilst I've used the mill to remove the bulk of the waste stock for the driver squares, this step could easily have been done with a coarse file. Much like the process of opening up the internal square in the flywheel, it just would have required more time and physical effort. And speaking of which, that's next. Starting with the centre hole position, I roughly marked out the square and then set about opening it up. Okay, so with the major bronze components on track, it's time to have a look at the shaft and drive handle. the handle is a straightforward profile, and again, whilst I've used a modern saw to save time, it's easy to imagine this sort of shape being cut with a simpler tool. And the same thing applies to the holes. They're not that difficult to form, nor do they need to be terribly precise. They could be made using the lathe tech of the day, or even made using much cruder methods like gouging followed by filing. To complete the part, I gave it a light sand, followed by a linseed oil finish. A bushing will ensure the smooth vertical motion of the drive handle on the shaft, and it fits neatly inside the diameter of the feeder that was cut from the flywheel casting. The holes in the shaft were formed on the lathe, and I've made the shaft as long as possible, while still keeping the overall length of the tool practical. This will help to minimise the effect of angular drift at the top of the tool when it's being used. Now the shaft ends would be a weak point of the tool if not given a simple reinforcement, and that's the purpose of the short ferrules located at each end. I've formed the ferrules to be a tight fit over the ends of the shaft, so that although they're firm enough to sit tightly in place when the tool is in use, they can, if required, still be slid off the end. The shanks of the collets have also been formed to be a snug fit inside the shaft, but they need to be cross-drilled along with the receiving end of the shaft to accept a retaining drive pin. The drive pin is a sort of thumb pin that can be easily inserted and removed by hand. The other end of the tool, of course, needs to be supported whilst in operation, so I've designed it to have a free rotating knob, easily held between thumb and forefinger. Now you may have noticed that I've used a shop-made drill bit for the last few drilling operations. This type of drill bit is incredibly effective at forming small, precise holes, and was being used by clockmakers for many hundreds of years prior to the invention of the modern twist drill. It's quite possible that its use extends all of the way back to antiquity, so it's a reasonable candidate for the sort of drill bit used to construct the Antikythera mechanism. I've created a separate video showing a process that could plausibly have been used to make this type of drill bit, so be sure to check out that other video. In any event, once created, the drill bits themselves can then be used to drill out the collets. Each of the 3 test bits correspond to a critical feature found within the mechanism. One is for a standard bearing hole, one for a standard retaining pin, and the smallest, coming in at 0.8 of a millimetre, corresponds to the ring of holes used to locate the calendar ring. Now, there is evidence of the use of soft solder within the mechanism wreckage, and certainly soft solder would be suitable to hold the bits in their collets. But equally plausible, and I think a little more convenient, is resin. I'm using shellac, but any hard resin available at the time would have worked well. The bit is solidly held, yet a gentle heat can be used to soften the bond, and permit the bit to be replaced or extended for sharpening as it wears out. The driving line needs to be securely fastened, and since this part of the tool is under considerable strain, I've turned up a couple of tie-off rings to ensure both a good solid hold on the cable and a modest distribution of the load around the hole. And with that, the tool is complete, so let's give it a test. It's interesting to see that the same practices that apply to modern drilling also apply to this tool. A centre punch mark is essential to ensure that the hole ends up where it should be, and a few light turns with the drill are enough to gently open up a good starting point. And of course, the entire drill pivots on that drill tip, so it has a strong tendency to follow the marked position. The driving action is quite straightforward. It doesn't take a lot of effort, just a consistent force to keep the flywheel moving. Although it does take a bit of concentration to keep the tool upright. It's easy to let the angle drift a little, and so risk wallowing the hole. The concept of using a pilot hole also transfers. The larger bit will cut through on its own, but it's much easier to pilot the hole first with a smaller drill bit, and then follow it with the larger bit. Now, one thing the tool needs is the ability to be able to vary its inertia and downforce as the circumstances change. So I made some extra flywheels of different sizes to give it that flexibility. The larger flywheel helps overcome the cutting forces experienced by the larger bits, and the smaller flywheel gives the tool more sensitivity for the smaller holes. And it's certainly a very practical tool to use. The change out of drill bits and flywheels is fast and easy, and the drilling time is comparable to a modern drill. Now, as to whether or not this type of tool was used to build the mechanism, well, who knows? But I do think it's fair to say that it's a contender. These test pieces compare well with the holes found throughout the wreckage of the mechanism, and certainly there's no doubt that the tool is capable of making holes to at least that standard. I'll continue to test it out and we'll see how it performs throughout the rest of the project. Thanks for watching. I'll see you later. Now, if you enjoyed this video and you'd like to help me make more, then consider becoming a ClickSpring patron. As a patron of the channel, you get immediate access to the patron series of videos. This includes the 5 videos from the wedge style hand vise build, and at present the first 7 videos of the Byzantine sundial calendar build. There's also the first 4 episodes of the new Tools Glorious Tools series, with more to come as that series progresses. In the most recent episode, I go through the things to consider when setting up your own home shop. And don't forget that as a patron, you also get free access to the plans for the patron series projects, so you can follow along and build them yourself if you wish. Visit patreon.com/clickspring to find out more. Thanks again for watching. I'll catch you on the next video.